So what is the top of the tree?
The root.
Yep. So the root is the node at the top of the tree. What's special about the root as opposed to any other node?
It has no parents.
Yep. No parents. Cool. So with this root, which is 1, what comes off of there? What's the structure of the rest of those two nodes, the 2 node and the 3 node?
The left and the right child.
Yep. How would you draw that like visually?
You'd make a branch off of the one going towards the left side and make that whatever value that you want to make that, and then do the opposite style branch on the other side, the right side. So make that 2, right?
Yep.
Root left is the 2 node, yeah.
Then what's here?
3.
Cool. That's our tree. Now I want to spend a little bit of time doing manipulations of this tree. So let's add some more nodes. 4 node equal binary tree node 4. 5 node equal binary tree node with 5. Let 6 node, that's right, I'm making a real cool tree. 6, let 7 node equal a binary tree node. That's 7. Okay, so I've added 4 more nodes. Here's how I want this to look. In this next level, I want to have my values set up in this manner. What should I do in order to get that layout?
Assign 2.left to be 4 node.
Yep, okay. So 2 node dot left equal to 4 node.
2.right equal to 5 node.
5 node.
Then 3 dot left equals 6 node.
6 node.
And lastly, 3 dot right is 7.
Thank you. Awesome. So now I've got this tree set up. How many levels are there?
3. If the root counts as a level.
Sorry?
Does the root count as its own level?
Let's say yeah for now.
3 levels.
Thank you, Sam. Thank you, Kevin. How can we count this?
You can go.
Oh, go ahead.
You can go down a branch until you hit 0, counting every time you go down.
Okay. Let's do that. So let's write a function that returns an int that starts at the root and goes down. Don't need t because we're not even going to look at the values. We're just going to be looking at left and right. So if I'm starting from my root, just go ahead and let me do what I want. Okay. We're not going to need the values here. We're only going to look at left and right. But here's the thing. Any tree right now, if we have no rules on them, if we just say you can make a tree, any tree can have any setup. This could be the setup of the tree. And so I can't just go down the left or the right side. I can't just say, go look for the leaves. What do you think we can do? I'm going to add this back in. We still have the same predicament. What are some ideas?
Use a recursive function to like go for each leaf node, I don't know, or a queue.
Yeah. So let's use recursion. Some of the suggestions you had were there. Use a queue. And what would you do with that queue, Albert?
You'll make a queue, and then you would enqueue the first node. Enqueue the first node of the tree into the queue, and then do a while loop, and then check enqueue the left and the right, and then dequeue, and then it will go through each, I think, something like that. So every time it's gonna enqueue a left node and a right node, and then it's gonna check if the left node has a left and a right, then it's gonna check if the right node has a left and a right. It's gonna, you can do a while loop until let's say the queue is empty. So while the queue is not empty, keep doing this until you find the end of it.
So how are you going to count the levels there?
If it's like left, count. If there's a value on the left, count 1, increment by 1, or right.
Okay. I think we could do something even simpler. But before we do that, what kind of algorithm is this involving? A specific kind of tree algorithm.
Depth search.
So the way this is going to work is it's going to enqueue 1, then it's going to enqueue 1's children. So it enqueues 2, then it enqueues 3, and then it'll dequeue 1, and then it'll enqueue the children of the next thing in the queue. So that's 4 and that's 5, and then it'll dequeue 2. So it's actually doing what we call a breadth first search. Breadth first search, which looks at all the nodes in one level before moving on to the next level. The queue is there to just say, all right, we're going to gather up all the nodes. And it just so happens by looking at left and right of the first enqueued node, it just so happens by logic that we're going to be adding each node in order in that row before we get to the next level. So the way the queue works, if we add nodes to the back, then as we start removing nodes at the front, the order we receive them in is the breadth of the tree. So by level rather than going down one branch and then all the rest of the way. We could do something like that. It would require a little bit of like counting as we go. We could also do something a little simpler. If the other kind of search is depth first, like Sam said, if I want to count the levels in a tree, I want to count the depth, right? That would be, those would kind of be matching cases, right? So for my depth first search, if I've got a root, all I want to do is potentially use this function recursively. How can I use this recursively? If this is the root, then how am I able to do it with anything that's not the root?
Setting the root to its children.
Yep. Treat the child of the root like the root in each recursive call. Right? The root is just a binary tree node. There's nothing special about it. And check this out. If I say 1 is the root, and if every node has either a left and a right, a left and a nil right, or 2 nils, then what should I do? Like, think about another recursive problem we worked on.
Could you repeat that?
Yeah. So the way we've set up our trees, they're binary trees. So there's potentially a left, potentially a right, potentially both, but also maybe neither, right? That's why it's optional. If that's the case, then to recursively traverse this tree, it's going to look very similar to another recursive question that we worked on. And here's a hint. We will probably need to, for each node, we'll probably need to call this function twice. Once for the left, once to traverse to the left, and once to traverse to the right. That's what our depth first search is going to be. What's a good base case here? How do I know when to stop looking?
If both left and right nodes are null.
So what do we call those nodes?
Leaves.
Well, leaves are actually at the end. For a given node,
Children.
the children are the left and the right nodes. And leaves are, these leaves right here are definitely also children. But for intermediate levels, they're always only children, not leaves.
Okay.
So we'll stop looking if children are nil. Cool. Anthony, how would I write that? Let's just say it's a guard statement. Anthony, are you there?
Yeah, I'm here.
Howdy.
So you want to have a guard node dot left equals sorry, guard root dot left. Hold up. You just want to have, I'm not sure how to write it, but you want to have a guard to make sure that the left or the right actually exists.
Okay. When would it not exist? Like what would be, if I went looking there, what would be the value?
I'm not sure what you mean.
Well, there's a 3-letter word for whether or not it exists.
Oh, right, if it's not nil.
Mm-hmm. Okay. Now we need an else statement. We want to do an else right now.
Wouldn't, I mean, we're returning the level, right? So if the root is level 1 and it doesn't have a left, wouldn't we want to return 1 as 1 level? Or
Maybe.
Should we keep a value that stores the levels
We keep,
and return that in that block?
well, we can do this recursively without saving a value, which is great. I promise. I love it at least. Here's the
Should it,
problem. Go ahead.
and the root dot right not equal to null?
Yeah. So if there are no children, so let me cheat a little bit. At the end, we're going to do our recursive call. And then that recursive call is going to be to both branches. We're going to add 1 for a specific reason. If I've got this tree and I look at the root, which way am I going to want to go? To the left or the right to find the highest level, the most levels in the tree?
The left?
Yep. And then let me add that stuff in. With this tree, I'm going to want to go to the right. That's great. That's from the root. So in the end, what I'm going to want to do with my recursive calls is I'm going to want to find which one is larger. So I'm going to want to see, was it larger? Did I get more if I recurse down the left side or the right side? And because this is recursion using the same problem, if I do it down the left side and I call the same function, it'll keep applying that same pattern. So if I'm now looking at 2, this node here with the value 2, if I go down the left or the right, I can see that, hey, there's neither, excuse me, it doesn't matter which way I went, both terminate at that level. So if I just say the level is 1 plus recursively calling this function down either side, all I need to do is say, well, pick the largest sum that I get.
How would you do that?
So just like we saw with putting arrays together on the recursive call with, what were we doing? That range problem the other day. All I would do is I would say return levels in tree from root dot left, root dot right. Let's put this together. Levels in tree from root dot right. And what I want to do now is I want to find the maximum of those. How do I get which one is larger?
You could do dot max.
Yeah. Do dot max. Like that?
Yeah.
Okay. Why is this not working right now?
You need a closure.
I need a closure. Well, I'm seeing a different error.
The roots are optional, so you need to handle that.
So the root is optional, which means there might not be a value here, but I want this to return an int. How can I change how this function is going to work? Because, again, remember, my recursive call is going to look at left and right of each child. And so 4 and 5, it's going to look for children as well. How do you think I should change my actual function call to deal with this?
Make the parameter optional.
Yeah. So since for each recursive call, we're going to only potentially be looking at a child, but we might be looking at nil. Let's just make the argument optional. And the reason I didn't fill anything in here is because we actually simplify the guard statement now. How do we guard that there is nothing here? So
Can
before,
you
go ahead.
ask that again?
Yeah, so before we were checking that our root, we were making sure root had left and it had right, but now we realized like, hey, we can just call this same function with an optional argument, and then what should I guard for here just to make sure that I haven't reached the end? Another way of putting it is, if our root is optional, what should I check before I do anything else?
That it exists.
Yep. I'm just going to check that root is not equal to nil. How do we feel about that? Albert, what's your thought?
It's cool.
Cool. All right, and then here is the next thing. If when we do call the recursive function, we go and we look at the children plus 1 level, then what should we return if we're not going down 1 level?
Zero.
Yeah, let's return 0. So if we make this recursive call, if we start at the root and the root is nil, then we just return 0. Here is that call. Levels in tree from nil. All right, this will just return 0. That. And that's what we want, because the next time we do this, if we are just at a root with no children, it'll return 0 plus 0. The larger of those is 0 plus 1. Recursion is amazing. Now let's fix this line. Let's make it work. The root's optional, so we got to check its right and its left. Let's see how we can get this max to work. What is max? I'll type it again.
An optional.
Yeah, it's an optional. But if the way we set up this function always works, we can put a bang on it.
Just bang it.
What? Go ahead.
Yeah, we could just bang it right there.
Okay. Why is this not working right now? Very silly, Swift mistake. What is max?
Maximum number on Swift.
Mm-hmm. But what does this error mean again?
Don't you need the parentheses?
Yeah, we need to actually call this function.
Also, for the levels in tree, you said that you can bang it, but isn't that saying that the root dot left and root dot right? So that doesn't necessarily have to exist.
Say that again.
You said that you can bang it, which you did, but the return thing is returning the levels in the tree from the root dot left and the root dot right, which don't necessarily have to exist.
Yep. That's a great question. So your question is, why am I putting a bang on it if potentially it could still crash with a nil?
Nil? Yeah.
Let me use proper Swift. Why am I forced unwrapping? Why am I okay with forced unwrapping max here? Let me throw that to the audience. What happens if I provide a nil argument?
Return 0.
Yep.
Okay, yeah.
Yep. So we return 0 for any nil argument to this function. Cool. How do we feel about this? Because this kind of recursion, this is when we say use depth first search, this is what we're talking about. Depth first search is usually a recursive traversal of the levels of the tree by looking at left and right. DFS goes down the tree recursively, whereas breadth first search goes down the tree kind of iteratively. And the reason I would call it iteratively is because it goes kind of like in a typewriter order using that cue that Albert mentioned. So look at this, and then I look at this, and I look at this, and then I look at this, and I look at this, and I look at this, and then I look at this. Because that is how the items actually get queued up. That's how I like to think about it. It's just one is definitely recursive, and the other is kind of imitating iteration. How do we feel about that? Cool. So let's make some notes. I will say a base case for most recursive tree functions will be if the item is nil. So by the item, I mean the node. Other variants, obviously this was the easiest one. Variants might be to see if the left and the right are nil. It was definitely easier just to check if that one item was nil here, because then we could just add things. So that was nice. But you will see a lot of people check their trees by seeing if left and right exist. This is a nice benefit of the optional in Swift, that we can do that. And then, in addition to the base case, we'll also see a pattern of, for the actual recursive call, is usually the same function for the left and the right side. So the recursive call in recursive functions for trees is usually that same function for the left and the right. There's nothing special, again, about left versus right. That's just the way that we are organizing information. By convention, we go down the left side usually before we go down the right side, but it doesn't need to be that way. The main, most important thing is from any node, there are 0, 1, or 2 children nodes. So this is an example of depth first search. We call it search even though we're not actually looking for one specific item, because it's the means by which we look through the tree. I want to take a pause here for a couple things. Any questions right now? Should we see if it works? Tia, do you think this is going to work?
I hope it does.
Me too. Well, if we look at this tree from our root, how many levels do we expect to see?
3.
Yeah. So let's check it out. Cool. That was great.
Would we need the +1 if we're not counting the root?
What would the situation there be? I'm not sure what you mean.
Like you said, in some cases you wouldn't count the root as a level.
Yeah, it's just by whoever's convention. If they say like, let's start counting from 0.
Okay.
Yep. Or another way of putting it might be sort of like an array. Someone might say, this is level 0. So they've started counting at 0, but there still are 3 levels. Yeah, that maybe is a little clearer.
Are levels usually counted as like indexes, like starting at 0, or?
Yeah, that's kind of what I mean, where like different people might have different conventions. I prefer to call this level 0, but people might say the root is level 1. It's probably easier to just count from 0. But there are 3 levels in this tree. How do we feel about this?
I think it's hard to visualize with both of the recursive calls in one line.
Mm-hmm.
But I get it's to like save space, I guess, instead of making the call twice and then comparing them.
Well, yeah, but that's a good point. How can we rewrite them?
What part are we trying to rewrite?
So this part is a lot, right? It says do a recursive call and do another recursive call and then find the largest number there and then add 1 to it. You could say let left levels equal levels in tree from root dot left. Who wants to take it from here?
The same thing, but right levels.
Talk to me. Tell me about code.
So you want to make a constant that's called right levels that is equal to the function called levels in trees, starting from the root dot right node.
Cool. So those are the 2 recursive calls. And then Sam, help me figure out how I logically return these, because this is kind of just a shorthand for a conditional in our case.
I mean, would you not, you would still compare both.
Yep.
So return left levels and right levels dot max.
Okay. What
Plus
else do we need? Cool. Say I didn't want to do dot max though. Let's do this in the extremely longhand way.
Can you use a ternary on this?
Oh, I love it. What could our ternary be?
Left levels is greater than right levels, question mark. So if left levels is greater than you, if that's true, return left levels +1. And then right levels +1 on the other side.
Cool. I like it. Does our computer like it? Still likes it.
Cool.
Cool. And so one more note here is going to be, because from any root or from any node, there are at most 2 children in the binary tree. There's a lot of either or going on, right? There's a lot of left or right. There's a lot of almost just true or false. So we're going to be doing a lot of comparisons. All right. So I want us to break out into pairs. I want us to practice a couple things. Here's the easy. This. So for the first one, find the leftmost node in a tree. So by that I mean find the leftmost leaf in a given tree. Then 2, using depth first search like above, find the largest value in a tree. And here's the fun one. I love it. Swap all leaves in a tree. So by swap all leaves, I mean swap them on their parent. All leaves for any questions?
What do you mean by swap? I'm confused by that one.